Okay, I mean, let's just get going, and if we get some stragglers, that's okay too. Let's say welcome to Richard, who's kindly agreed to speak to us from Georgia Tech. Richard is going to talk about solving sparse linear systems faster than matrix multiplication, which is a completely amazing result in my opinion. I hope it's okay I say that. But Richard has also done lots of other great work. He did sort of the first paper that started to clean up this major result by Spielman and Peng on Laplacian solvers. And sort of in this way, I think, caused a lot more people to think about this, which grew into the whole Laplacian paradigm. He's also done lots of other amazing work on Laplacian solvers. The first parallel Laplacian solver, the first solver to be faster than comparison sorting. And he's done some very nice work on parallel graph decomposition, solving directed Laplacians, which I think is completely amazing. Lately, also a very nice result on short cycle decomposition. I hope it's okay I list all these things, Richard. I'll stop now. And also lately, lots of exciting results on dynamic graph algorithms. So with that, Richard, I'll let you start.
Okay. Well, thank you, Rasmus, for the introduction. And I'll be thank you to everyone for tuning into this talk. I'll be talking about a recent development in getting faster solvers for sparse linear systems. I will be doing this talk with a little bit more detail on the mathematics. Unfortunately or fortunately, this is algebraic mathematics, which means that in my own experience, it's very easy to get lost. So if there's any point, because the problem is that there is just a whole bunch of notations. So if at any point the notation ever gets confusing, please interrupt and just let me know that, hey, go into more details about this. My own experience with this stuff is that it's a little tricky to catch up once there's something that's confusing. But please ask questions, because chances are, if there is that I'm taking for granted, probably half the audience have the same question. So please interrupt with any kind of questions you have.
And I'll just add the quick comment that we have this nice question feature and live chat also, and you can add questions into both, and we'll try to make sure Richard is alerted to questions that have...
Okay, so I'll start with the problem. So I have a linear system. I have an n by n matrix A with n and z non-zeros, input vector B, and I want to get x such that ax equal to b. So this is a problem that has been studied extensively in engineering, management, and data science. So some of the earliest examples of this are the stress diagrams needed to compute forces. So this is a diagram of the energy that the force. It's a force diagram of building a cathedral. In management, you have things like there's even very early computational devices, things like Abacus, which comes with algorithm for solving systems of linear equations. So this is for partitioning things, for dividing things, and for like the routing of goods. One of the earliest examples of using linear system solving in data science is the identification of orbital mechanics. So the idea that orbits are ellipses. So there's all sorts of work on once you have ellipses, you have to kind of fit points to an ellipse, which is one of the earliest instances. So with computers, these things essentially this is a very US-centric view, but at least in the US, these things essentially correspond to 3-letter and 5-letter agencies. So if you're interested in high-energy particle simulation, sending an entire logistical chain and also their associated logistical chain across the world, or predicting the outcome of the election, there are, I mean, I go into more details about these applications in a talk that is also recorded online, and there are also all sorts of other ways to just search linear system and then want these keywords, and there's a bunch of these. But for this talk, I want to focus on the mathematics. So I want to focus on the question of the running time of this algorithm. So one of the most well-studied of getting faster running times is to compute the inverse of the matrix A, or some representation of it. So starting with a work by Strassen, the focus in worst-case algorithms have very much been on faster matrix multiplication. And this runtime is known to be n to the omega. So there's actually some equivalence between inverting a matrix and multiplying a pair of matrices. But there are also other forms of intermediate representations. But in terms of just computing A inverse, the runtimes have been, so Strassen got to 2.8. Strassen got to 2.8, and then Coppersmith-Winograd got to 2.35. And then over the decade, there has been a lot of work that got this number gradually down even further. So right now we're still at about 2.37, 3372860-ish. Some of the other caveats of this algorithm is that it's about n squared memory. So this works roughly until you run out of memory. So that's anywhere between 100,000 to a million by million matrix. What's common in practice, though, is it's very common for us to have linear systems with about 100 million to a billion dimension, and then non-zeros is anywhere between a billion to, say, 100 billion. So, so there has been a lot of work on getting even faster algorithms, and these works they actually started with the assumption that my linear system is a grid, because in scientific computing, right, one of the most common ways to get large linear systems is you take your space, you partition into grids, and so on. So this led to a line of work on nested dissection, which is the idea of using recursive separators to speed up to restrict the elimination structure. That line of work, though, drew a very direct connections with graph theory. In that, once you're thinking in terms of non-zero structure, there's a very direct correspondence between the non-zero structure of matrices and edges of a graph. So then this led to work by Vijaya that started this line of work that Rasmus talked a little bit about at the beginning about using structures in your matrices or structures in your linear system to get faster algorithms. And that line of work essentially eventually got to runtime. Actually, I think that is out of date now because I have not seen the paper yet. But yeah, this number is as of 2014. That's the current fastest runtime. If your system have graph theoretic structure, I think there are improvements to this in an upcoming conference. But the other question is, what about beyond graphs? What can we do beyond graphs? So the graph theoretic ideas actually have been extended to all sorts of other systems which are structured, but are not exactly graphs. So things like the truss system, which is these stress and strain diagrams. You get to directed graph. What about directed random walks? You also get the situation where instead of working with real numbers, you have complex variables. So what about extending into complex and so on? One of the big surprises that happened in this area over the last 5 years are these results that say that some structures are complete. In retrospect, if one dig all the way back into the optimization literature and look at the completeness of linear programs, in some sense this is not like. In some sense, this is there's some strong hints that this is the case. In that, back in 1979, there was this result by Alon Itai who showed that two-commodity flow is complete for linear programs. Of course, that's for linear program that's in the exact setting. So getting this to work for two commodity Laplace, for these graph theoretic things under kind of numerical convergences took a lot of effort, and Rasmus and Peng in 2017 showed that two commodity Laplacians are in fact complete for linear systems. What that means is that if you have a faster solver for some of these graph theoretic matrices, you actually have fast solvers for everything. This then got extended to a lot of these other structured problems. So Rasmus, D1, and Peng in the past SODA, what they showed is that positive linear programs. So this is linear programs where you have all the entries in your matrices are positive. These are actually problems that there has been a lot of work on getting faster algorithms using these with independent algorithms for. They show that these are also complete for linear systems. So recently, there have been a lot of these completeness results that say that, hey, this type of structure is actually not that useful. This type of structure, if there is progress, it will let us solve everything. So the linear system type complexities, especially in the sparse case, actually have been used as a hardness assumption in showing hardness for some of these structured instances. So formally, the way that this is phrased is the sparse linear system time hypothesis, which states that linear systems with condition number nnz to the little o of 1 cannot be solved in time that is about nnz to the omega. And what I will talk about in this talk is a result that refutes this conjecture, the value omega. So in the paper, they work with SLTH2, but what you would get from sparse matrices using multiplication. So formally, what I will talk about is that matrix multiplication exponent of omega that is roughly about 2.373. We can solve polynomially conditioned systems with nnz non-zeros to a 1 over poly in time that is roughly nnz to the 2.331. So it's roughly a 0.4 improvement over the exponent of 2.37. So the precise running time that we get is this term, which is 5 omega minus 4 divided by omega plus 1. And then there is log squared kappa. So what is this kappa? What this is actually the max singular value divided by the mean singular value. But I haven't even defined all of that. It's a little tricky to define that for general asymmetric matrices. The way that you can think about this, I will talk about how to do the reductions on a couple of slides, but one way to assume this is that you can assume that A is symmetric. This is not hard to get because you can just do A transpose A. You can assume that the number of non-zeros is just roughly n. So we're talking about just extremely sparse case. So n poly log n is the kind of sparsity that we need. And then you can assume that basically the max and min eigenvalues are within poly n factors of each other. There are two main pieces to this algorithm that I will focus on. One is a block Krylov space method. So this is a generalization of the conjugate gradient method, and I'll talk about this first because this is the main algorithmic component. The part that I'll try to focus more on in this talk is the notion of matrix anti-concentration, namely showing that a random matrix is expected to have a large singular value. Before I talk about what we do, I should also mention some of the caveats that we do. So the first thing, well, both of these pieces, I believe they are actually fairly major caveats with them. The first is that for the block Krylov space method, despite what I was saying earlier about n squared memory, the way we prove this algorithm, we still need n squared memory. Except we don't store n squared numbers. We actually store subquadratic number of numbers, but the way we do this is that we keep a lot of digits. So every one of the numbers, we actually have to keep a lot of numerical precision for this to work out. Which then leads to the second issue, which is that I really don't think our precision analysis is optimal. So in the matrix anti-concentration, there are a lot of epsilon nets around, and things are just not very optimal. Did I just lose my slides?
It looks like we lost the slides.
It says my connection is unstable, so let me put this back up. Okay. Oh, I lost connection for a second. Yeah. Uh-oh. Okay, should be back now. I'll continue then. So what I'll talk about is then I'll just basically talk about the algorithmic aspects and then the more analytic aspects. So I'll start with the algorithms, which are based on what's called Krylov space and Hankel matrices. So the algorithm is a version of the conjugate gradient algorithm. So what a conjugate gradient algorithm is that it's an iterative method. And it solves ax minus b by doing gradient descent on ax minus b 2 norm. So it's essentially the kind of the modern way to, especially with optimization in mind, the way to think about this is that it's essentially just doing gradient descent on the function ax minus b. And then the idea is, so the main thing that makes conjugate gradient interesting is that it picks the steps adaptively. So it's basically picking, so the gradient of ax minus b 2 norm is essentially ax minus b with some constant rescaling. And it's picking this alpha x, the step size adaptively and in an optimal way. Formally, what it says is actually it picks among all possible coefficients, it actually picks the best sequence that minimizes this 2 norm. So the idea is that notice that once you have ax minus b, your next step is just a times ax minus b. And then the one after is a times ax minus b. Well, it's a times ax minus b. So these are actually all low degree polynomials of a. So it essentially picks the best solution in what's called the m-step Krylov space, which is basically you take the input vector b and you just take all linear combinations with a. So you're solving b, a squared b, all the way to a to the m minus 1b. And the behavior of this algorithm is such that if you combine this kind of optimality claim with things like Chebyshev polynomials, which says that for numbers in the range of lambda max to lambda min, there's good interpolance. It essentially gives an algorithm that runs in time that is square root of the condition number. So you get square root of lambda max divided by lambda min, which is a large number when all the eigenvalues are in some poly n range. So this could actually be a poly n factor overhead. And in practice, the way that people deal with these very ill-conditioned linear systems is that they do some kind of preconditioner. But the way to reduce these condition numbers, they tend to be fairly tricky. The one that we use is actually from the original conjugate gradient algorithm by Hestenes and Stifel, which what they say is that we just let m equal to n. So now once m is equal to n, you can show that this space, this is the n-dimensional space. It's a basis for the entire space of vectors. So this gives you an algorithm that runs in nnz times n time, but assuming exact arithmetic or over finite fields. So there is some very strong hint that in some model of computation where you ignore all numerics, these are n squared time algorithms. And over finite fields, we do get this number. But once we once we get to floating point numbers or the kind of the linear system settings, the issue of numerical stability or numerical precision kicks in. So the way that we view conjugate gradient is that it's essentially doing a linear regression on the m-step Krylov space matrix. So the way you can think about this is that you just generate all the vectors, b, a squared b, all the way to a to the m minus 1b. And the problem is that if the numbers in A are as large as order m, well, they are as large as poly n, once you power it to n times, you're going to get numbers of on the magnitude of n to the order m, which means your numbers have about m digits if you do m steps of Krylov space method. And the issue that comes with this is that n steps of exact conjugate gradient, instead of having nnz times n time now, once you factor in the bit length, you're looking at nnz times n squared, which is a cubic time algorithm. So there have been a lot of attempts at addressing this issue by reducing precision in some ways. But unfortunately, there was this paper. Well, there was this paper there was this recent paper by Musco, and Sidford that really clarified this issue. They actually showed that many approaches for fixing this are still problematic in the worst case. They actually gave a kind of a very unified treatment of all the ways that have been proposed to kind of locally fix these interpolants and so on. So the generic kind of assumption we made is that if you do all m steps, this is just tricky. So what do we do instead? What we do instead is we're based on the block Krylov algorithm. So the idea is that instead of working with a single vector and with a very large value of m, what we do is we pick a small value of m, but we pick a lot of vectors to start with. So we pick some sparse n by n over m matrix G, and then we generate this m-step Krylov space method. And then because the numbers now, they're instead of being n to the n, they're just n to the m. The extra factor of digits is just m, right? So we think of m as some small number, so like n to the 0.1 or something like that. Then you get an nnz times n to the times m times poly m. And then the other key thing is that we work with n times n by m matrices, which by things like rectangular matrix multiply, you get runtime that is essentially n times n over m to the omega minus 1, but then times the bit complexity of m. So we get runtime that looks like the following. We get runtime that essentially look like, assuming a sparse matrix, we get n squared times poly m plus n to the omega times m to the 2 minus omega. And notice that this exponent is negative. So 2 minus omega is negative. And this is a positive, but this has n squared. So by somehow tweaking just by adjusting coefficients, you get an algorithm whose runtime is somewhere between 2 and omega. And that's essentially where our running time is coming from. Of course, algorithmically, the most tricky part of this is how do we essentially work with n by n over m matrices. And here we build upon this idea by Eberle, Gisbereshit, Georgi, Sorohan, and Villard. And what they were working on, this idea was actually initially developed in computing the inverse of a matrix over a finite field. So like a matrix mod P. They were able to show a faster algorithm. And the key observation is that the gram matrix of a block Krylov space matrix is very well structured. In fact, it's what's called a block Hankel matrix. So what is a block Hankel matrix? A block Hankel matrix is a matrix where everything on the diagonal, so you take a matrix, you take the diagonal, you take all the diagonals, they all look the same. Why is K transpose K? So why is the gram matrix of the Krylov space matrix block Hankel? So the way you can think about this K transpose K is you take the ith column, you take the ith column block, you multiply against the jth column block. What is the ith column block? It's a to the I times g. Jth column block is a to the j times g. Transpose, you get that AB transpose is B transpose A transpose. So these A's actually get put together. So essentially the ijth block is G transpose A to the I plus j times G. Notice that this is a number that only depends on I plus j, which means that if we just look at, so entry 1, 2, and 2, 1, or entry, say, 5, 2, and say 3, 4, these are all the same. As long as I plus j is the same number, you get a lot of symmetry in your matrix. So pictorially, what it looks like is that it looks like a matrix where these diagonals look the same. And here, there's a quick way to see that this kind of matrices, you can do a lot of operations faster. And this is easier to see in the forward direction. So when you do a matrix vector multiply, what happens? If you do a matrix vector multiply, what happens is that entry ij is just the mij block. Well, the hij block times hj. What is the hij block? It's mi plus j minus 2 against xj. And the observation from this is that this is a convolution. Well, it's actually a shifted dot product. So what you take the sequence of x, you take the sequence of m, and then basically hx of I, what it is the first shift, the second shift, it's the ith shift when you take the shifted dot products. So these are essentially some kind of convolution. And you can do this in about order m matrix vector multiplies in the blocks instead of order m squared. So you can get runtimes that is proportional to the size of your blocks times m. And that's the runtime that's underneath a lot of these things. So this kind of ability to do fast matrix vector multiplies naturally leads to the question, can one solve these things faster? And in fact, there has been a lot of work on this. So KKM79, I think this is Krylov, Korn, and Morph. What they showed is that you can get to what's called fast solvers. So in numerical analysis, they term a fast solver to be one that is n squared time. And then they term things that run in nearly linear, so n polylog n time. This is called super fast solvers. So I mean, this is not in the non-block case. So this is just instead of having block matrices, they're just a single numbers. So there's fast solvers, there's super fast solvers. Mead Anderson came up with the first super fast solvers. Those run in about n log squared n time. And recently there have been some work on getting super fast and stable solvers. There has also been some work on super fast and stable solvers for block case. Well, there's some combination of super fast, stable, and block. And there has been work on combinations of this. But for all of these, from what we could find, if you happen to know more pointers, please let me know, and I'll be very happy to look more into it. But for the ones that we could find, even the ones that are stable, the issue is that their dependence on the bit complexity is not linear. Their dependence is actually quadratic. So in the paper, what we do is we actually give a super fast stable algorithm with number of arithmetic operation that is O tilde m times just n over m to the omega. Omega minus 1. That's important. Yeah, this should be omega minus 1. And basically on numbers whose size is basically log of the condition number. So we actually, that's not cool. Yeah, so we actually get algorithms whose runtime, basically super fast solvers for block Hankel matrices that are significantly more stable than previous ones. And here the key idea is actually from the KKM paper, which is the notion of a displacement rank. So displacement rank, what it says is that if I take my matrix and I just shift it downward, so I shift it to the left by some shift size s, which is actually just the size of the block. What you can show is that for Hankel matrices, after this shift, you subtract it against itself, it's low rank. And the key statement from KKM is that if an invertible H has low displacement rank, then H inverse is also low displacement rank. This is very significant because it says that not just the Hankel matrix itself has succinct representation, but also H inverse has a sparse or has a small size representation. As a bit of a aside, I just want to kind of derive this just to give an idea how this comes from. So the way you can derive this is you can just write down these shift operators, and you can write down the displacement rank operator as the rank of just H minus delta H delta hat delta transpose. And then because H is invertible and the rank of matrices are preserved under invertible transforms, you get that it's equal to the rank of I minus H inverse delta H delta transpose. And then the key fact is that for any matrices A and B, notice these are not invertible matrices anymore. It's okay if these are not invertible matrices. What you can prove is that rank of I minus AB is actually equal to the rank of I minus BA. So then what you do is you just take this as your A, you take the second half as your B, you swap them. So now you're at I minus H delta transpose H inverse delta. At which point, notice that it's the H inverse that's sandwiched around the deltas now, and then you multiply by H inverse again, and it comes out to be the rank minus H rank of H. Is everyone okay with that proof? So what I'm trying to show here is that as soon as you can conclude that one of these matrices in the forward direction, so their original representation has a small size, you can conclude that their inverse also have very small representation sizes. And this is significant because now we have basically both small representation for the matrix as well as inverse. And we can kind of just apply this kind of stuff recursively. Gonna give a couple more seconds on this slide because this is kind of the most critical slide for the algorithm, is that it essentially says that once you have the block Krylov space matrix, you can basically get small size representations of its inverse. And then the way you use this, as I was saying, is just basically you recursively apply this. And here I just kind of want to pause and say that the reason this kind of stuff works is that there's this kind of fairly general phenomenon that once you're able to get these small size structured representations of things, you can kind of start recursing them into each other, and essentially you obtain runtimes that is basically what you would get from basically as if you had them to start with. So this is kind of where one can go from a structure to an algorithm. And here the idea is basically just do some kind of recursive block Cholesky or recursive Gaussian elimination type algorithm. This type of algorithm, this is present basically throughout the Hankel matrix literature. So the original KKM, the Bitmeter-Anderson papers, they all do this. We based our presentation on this paper from a couple of years ago with Rasmus, Intat, Sushan Sakardeva, and Dan Spielman. And the reason we base it on that one is that it gives a much better handle on how the numerics propagate and how like approximations come in. But the general idea is you just take a matrix, you take your Hankel matrix, you partition into a prefix and a suffix, and you just recursively generate a small representation on the top left block, and then you generate the eliminated component of the bottom right block, which actually is another block Hankel matrix. And then you just recursively generate the small representation of this. So you solve on this, and then you combine this inverse with this inverse, and you bring back the overall small size inverse of H as well. So basically the short version is still a recursion more or less happened. And then the overall algorithm, what it looks like is we generated an n times n over m sparse Gaussian matrix. We take this Krylov space, which is G, A squared, G, and so on. We build a Hankel matrix from it. So the runtime of this is essentially n times n over m to the omega minus 1 arithmetic operations. Build a solver for H, and then we just return the the solver is basically the inverse of this object. So what we do is to get rid of the k and the k transpose, we just multiply by k and k transpose, and then we apply it to the vector b, and that essentially gives the solution vector. So this is essentially what the overall algorithm is. For the runtime, first the thing to notice, construction time is essentially n times mn times nn. So in the sparse case, it's essentially about n squared m cubed. Yeah, this is not very accurate. This is assuming basically a sparse matrix, and The runtime essentially comes from, there's a couple of steps. There is a step where you build the Krylov space matrix, and then there's the step where you do the K transpose AK. And it's this step where you get the blocks of the when you get the blocks, you have to do a G transpose A to the I times G, which is where it's expensive. But then when I solve for H, the key thing is that we need to keep about O tilde m digits. So then you get a runtime that is about n to the omega times m to the 2 minus omega. So now you balance this n squared m cubed against this n to the omega m to the 2 minus omega, and you essentially get that for omega that's 2.37. The m value you set to is about 0.11. And the reason this works is that 0.11 cubed is about 2.33, and then m to the 2 minus omega. What is m to the 2 minus omega? 2 minus omega is about 0.37, so that's about a third. So you get about this divided by 3, so that's about 0.4, and then you get the speedups. That's also the speedups you get over n to the omega. So at a high level, I just want to kind of mention why is this faster. What we essentially did is that we replaced multiplying n by n matrices with convolving against m matrices of size that is essentially n over m by n over m. So what we did is we replaced a big matrix multiplication with a bunch of convolutions on numbers that are fairly large. So the numbers themselves, they have m digits. So essentially we replaced 2 of the dimensions of Gaussian elimination with essentially some kind of fast convolution. And we showed that, and the key thing that we actually need to show. So the other thing to notice about this is that it's actually numerically very, very precise. Like the numerical room for this is actually not very big. In that if you get an algorithm where the dependence on the bit complexity of what's in between is about m, you're good. But if you're about m squared, or even more than like m to the 1.5, this actually would be too much. So m squared digits would actually be too much. So for the rest of this talk, I want to focus on what we talked about in the numerical aspects. So how this numerical precision is coming about. But before I continue, any questions? Okay. So the main kind of mathematical difficulty of this result is that we want to bound the number of digits needed when working with this Krylov space matrix, which is g a squared g all the way to a to the m minus 1g. So the main difficulty is bounding the numerics of working with this Krylov space matrix. And this is a quantity that was studied before as the growth factor of matrices, and it was a kind of explicitly studied in smooth analysis. And what they realized is that it's exactly dependent on up to a poly n factor, which is basically log n additive digits. It's exactly dependent on the ratio of the max over min singular values of k. So the max singular value. So you can think of the max and min singular value as if I have a unit vector x, how big or small does kx become? And the max singular value, it turns out to just be poly n of the max entry. That's not very hard to see because you only have n squared entries, triangle inequality. For a unit vector, you get that it's basically the max magnitude of entry. The min singular value is where one has to be very precise. So the min singular value is basically x, where x, the norm of x is at most 1. So this is all 2 norms. And then I want to basically minimize kx to the 2 norm. So the max singular value, by what we talked about before, right? Because all the entries are poly n, the max singular value just n to the order m. The min singular value is where all of our effort are spent. So the formal bound we prove is we actually have to perturb A a bit. So there's a bunch of perturbations. And the reason is just that if A have duplicate eigenvalues, things are bad. And we also want A to be symmetric. So what we show is actually we show that for any input matrix A that may not be symmetric, what we can do is we can take A transpose A, well, A bar transpose A bar. A bar transpose A bar makes it symmetric, and it actually keeps all the things you want for linear system solve. We perturb it by a sparse Gaussian matrix. Actually, plus minus 1 is even okay there. The initial perturbation, there's a lot of flexibility, but the main thing is it's just an additive sparse perturbation. So we just pick log n non-zeros per row, we just add a bunch of noise to it. And we perturb by something like n the negative order log n to form A, so that for m step Krylov and s block size, we can't let m times s equal exactly n, but we let ms equal to n minus little o, n minus order m. So there's actually a little bit of extra slack there as well. So then we take a Gaussian with about m cubed non-zeros. And what we get back is a block Krylov space matrix. So we get this matrix G, A squared G, and all the way to A to the m minus 1G. And we can show that with high probability, for all unit vectors, Kx 2 norm is at least exp of about m. So there's also a bunch more log factors on this m as well. But what we essentially show is that with a couple relaxations, that's where all the algorithmic overheads come from. We're still able to get a runtime that is roughly, well, we're able to get a bit complexity that is ZXP negative O tilde m. Any questions about this statement? Okay. So to give some idea how we prove such a statement, it is useful to first think about how to prove the lower bound on the mean singular value of a entry-wise IID matrix. This is the setting that was addressed in the smooth analysis papers. This was subsequently also looked into in a lot more detail and by Tao and Vu. And I think it's really the Tao and Vu paper that got the right kind of approach for this. I should also mention that there are papers by Rudolfson and Verschainen that essentially even got the constants. So they not got only the exponents right. I think they even got the first order constants for these things correct. But what they showed is, the way they show these things is that they look at one column of your matrix M. So let M be my random matrix. And all my entries of M are IID normal. And if you look at one column, so what you prove is that you observe that for any unit vector x, there is some entry, xi, where the magnitude is big, right? You only have n entries. So there at least is one entry whose magnitude is roughly 1 over square root of n. Consider that column I. Imagine generating this column last. If you generate this column last, there is a direction that's normal to all the other columns. This is where you use the fact that all the columns, you have fewer than n columns. So there is some null space of the other columns. You take any vector, you dot it against a random Gaussian. So random Gaussian, the way you think about it, is just it's a uniformly random direction. Its dot product in that direction is 1 over poly n with high probability. So the part that in column I, that is orthogonal to the rest of it. So basically there's no way to remove anything from, no matter what combination in the other columns you take, there's at least 1 over poly n of this column that just cannot be removed. So you prove this with high probability you prove this for every column first. So you prove that for this matrix with high probability over all columns, each column is reasonably independent of the rest. Like each column has a lot of things, has a non-trivial portion that is orthogonal to the rest of the columns. Once you prove that, what you say that, hey, my X has a big entry. In that entry, that column, so I multiply the part that's orthogonal by the magnitude, so you get about n to the negative half divided by poly n. So you conclude that the mean singular value is 1 over poly n. Questions about this proof? This is essentially the proof template we use. Well, we try to do the same thing with randomized block Krylov space. We observe that each column of G, so before we did our Krylov space, we did G, AG, all the way to A to the m minus 1G. Think about this instead as the first column of G generating a Krylov space. The second column of G generating its own Krylov space. But these are all m-step Krylov space now. So formally the K of Y is just y all the way to a to the m minus 1y. I'm gonna turn off my video because I think my connection is being flaky again. But what's happening here is that every column of G essentially creates a m-step Krylov. And what I'm generating is I'm generating an m-step Krylov space for a single vector. And now notice that each of these vectors are independent. So what we want to prove is we want to prove that every one of these blocks have a lot outside of the span of the rest of the blocks. So formally what we show is that we show that imagine generating the other blocks first. So we generate blocks, well, the other columns of G first. So imagine generating columns 2 to S of G first. We show that for all unit vector X, W transpose the first Krylov space times the vector X has about size 1 over, has size essentially exp negative order M. So essentially we give kind of the matrix version of this big dot product kind of statement. What's happening on each block? What's happening on each block? So to get some intuition on each block, the first thing to notice is that if G is just a dense Gaussian, so if G is just instead of think of Kg instead of thinking about it as a kind of this block matrix, think about it as a Gaussian matrix. You can actually show that it's not hard to show that the probability. Well, actually, you have to show this for a single vector G. Yeah. So just think about the first column of G of Kg, right? That's just a Gaussian vector. The probability of a Gaussian vector being big is at least exp of negative dimension. So you can kind of think of some kind of like epsilon I type net type argument. But there's two main caveats that we have to deal with on each block. The first is that the entries are correlated. The entries in Kg are highly, highly, highly correlated. They are G, AG, A to the m minus 1G. The entries are like, every column is correlated with the previous ones. And the second issue is that G is sparse. The correlation is actually the bigger issue because for the dense and sparse, at least they are in the follow-up works in the works inspired by Tao and Vu. So these are, Kyle Liu has done a lot of stuff on this. They actually showed that a lot of these ideas do extend over to sparse vectors. So sparse we can kind of deal with. The issue with the correlation is much more problematic. Let's first deal with the case where A is a diagonal matrix. So the case where A is diagonal, you can just think about it as A just has a bunch of lambda. So A is equal to basically a diagonal matrix. That's exactly the eigenvalues. So then what is Kg? Right? Kg is just G and then lambda G, lambda squared G all the way to lambda m minus 1G. You can actually write down exactly what is Kg. Kg is just Kgij is just lambda I to the power of j minus 1 times Gi. Notice not Gj, it's actually Gi because when we apply one of these matrices to a diagonal matrix applied to a vector, we just do the row and row. We actually just match up the rows. We can actually think about this as G. We can actually pull out the G now. So notice that the first row is rescaled by G1, second row G2 all the way to Gn. So it's actually diagonal of G times this matrix, which is what's called a Vandermonde matrix. So it's the m-step Vandermonde matrix. And so in general, what you're getting is, in general, you can apply this to kind of to the spectral decomposition of A. So instead of just diag of G, what you get is diag of UG where U is the eigenspace, so the kind of the change of basis for the eigenvectors of G. And then what you get is that Kg is the diag Ug times the Vandermonde matrix of the eigenvalues. And with Vandermonde matrix, you have this very nice property, which is that you can actually exactly write down the inverse. Because it's a polynomial, it's essentially polynomial interpolation. So observe that if you multiply by Vandermonde matrix, you're essentially just applying coefficients to a polynomial. You're essentially treating the x as the coefficient, and what you get back is you're just evaluating a polynomial at a bunch of points. So the reason this is useful is that you can just write down exactly what is the inverse, and you can show that as long as there's no duplicates. If you have duplicates, things are bad. This is why we have to kind of initially perturb the A. So as long as the lambdas are 1 over poly separated, you can show that for any x, every subset of S by S block, so every set of M by M block is actually reasonably invertible. So what you can actually show is that you can show that the Vandermonde matrix for any vector x, the Vandermonde matrix has a lot of large entries. So what we want to show is we want to show that for any vector x, so this entire stack of matrices multiplied by against x has large entries. And we want to show this over all possible G with high probability. We can unwrap this a little more. So the next thing what we can do is now we just do a full epsilon net on vectors x. There's only about m of these, so we do an exp order m size epsilon net on all possible x. And we show that for each corresponding y, we are extremely unlikely. So we want to show that exp negative O tilde m probability that we have a G that is bad. And the reason this is a good idea is that once you fix a y, you can actually permute the role of this. We can unravel this U matrix. So here you use the fact that diag of A times B is equal to diag B times A. So what happens is you can basically pull the y into the middle. Instead of having G in the middle, now you get W transpose diag Y, U, and G. So, and now the thing is that because Y is fixed, U is fixed, W transpose is fixed. You can actually combine them into a single matrix. And we are back to our initial problem of we have this fixed matrix W transpose diag Y times U. And we want to bound the probability of a particular G giving a small dot product against this matrix by something like exp O tilde M. And this is where the full block basis doesn't work for us. The reason is that if dimension of M is at most negative M, we can only show a probability that is roughly exp of negative dimension of W, failure probability. But the number of Y or the size of epsilon net is exp O tilde of M. And this is what necessitates this kind of idea of leave a whole bunch of extra columns. So we leave about O tilde M extra columns. And then the number of rows of W actually exceeds. So the number of rows of W then exceeds the number of the number of Y's we have to think about. So the way that algorithmically this gets realized is that we pad with a dense Gaussian matrix. So algorithmically what we do is we pad this with a dense Gaussian matrix. And we pad this with a dense Gaussian matrix, and we get about extra columns, and we deal with that by doing another block Cholesky type algorithm. So formally for sparse Gaussians, there's actually a couple more things we need to do. One, we need to use epsilon nets to rule out any vector W where these things are sparse. Basically, have to make sure that W is also very dense. We do a epsilon net on the row space of W to show that because G is also a sparse Gaussian, we actually sample down the things. So we show that the sparse the non-zeros we pick still has good large mean singular value. And then we apply restricted invertibility to recover a well-conditioned structured submatrix. And then we basically get the exp O tilde M bound we needed. And that gives the overall, that then plugs into the size of the epsilon net, and we get the overall probability. So that's essentially how the proof completes itself And the reason I'm pointing out this is that it gives you kind of idea where the m cubed comes from. And with that, I can kind of lead to some of the open questions. The most immediate I feel in this direction is just, I think G with O tilde m non-zeros per column also works. And should that work, that would refute SLTH 2.27. So it will give a runtime that is about 2.27. The kind of the more intermediate questions I see is it possible to get to SLTH2? To get to SLTH2, there are these results that says that using, for direct methods or matrix inversion methods, you can actually have logarithmic dependence on the log of the condition number. You can actually get log bit complexity. And the idea there is that one have to kind of look a little bit more into the representations of floating point numbers. So there's kind of different ways of looking at doubles or floating point numbers becomes extremely useful. The kind of the most kind of ambitious questions in this space I see as getting below NNZ squared. So here there's some very intriguing connections pointed out by this algorithm, which is that it's saying that a lot of these things, it's useful to look at the finite field cases. Is it possible to solve Laplacians over Z2? It's like for any other one of our structures. So we basically took the structures coming out of numerical analysis, scientific computing. What about the structures that come out of theoretical computer science? What about things like Laplacians? What about things like the dense case? Can we somehow devise some kind of sparsification? And there, like even for intermediate condition number, I feel these questions are very interesting. And with that, I'll stop and take questions. Thank you for listening.
Thank you very much, Richard. I can see some people have figured out how to clap. And now I know too. That's very interesting. Now, people, if you want to ask questions, you can type them into the question part of the. You see the sort of a question chat. You can also ask us to put you on video if you want to just ask your question in person. So maybe I'll start off with a question while people think about whether they have any. So can you say more about what you think you might be able to gain from having a good floating point analysis regarding the second point?
Oh, the second point, so condition number dependence.
Yeah.
So one of the kind of the most intriguing things here is that you're doing matrix multiplication, but you're doing a lot of matrix multiplication involving fairly large numbers. So in the exact case, if I'm multiplying matrices with m numbers, like by like mod p type arguments, you can actually show this is equivalent to multiplying m independent matrices, like m matrices that have nothing to do with each other. Mm-hmm. So in the exact case, you don't gain anything because multiplying a batch of matrices is somehow equivalent to multiplying like one matrix. But the thing to notice here is that there is a lot of room for error. Like none of these things are very precise. So, I mean, at the end of the day, there's only something like negative, like you only need about n to the negative order 1 precision. So there's actually a lot of room for kind of different, there's a lot of room for other kinds of round-off errors. So the question there, I mean, the one that seems most intriguing is that if you are allowed some correlation, like you are allowed to have error, but like error in like a controllable correlated way, but just not in the worst case way, and you want to basically multiply a batch of matrices, could one get any kind of gains? So the condition number dependence, what I really meant is just that some of these algorithms, when you have an overall nice condition number, but your intermediate numbers are bad, it's not necessarily the case you have to use the worst case complexity. Like, I mean, I would hazard to guess that if one just implements this type of algorithm, the intermediate number of digits that one has to keep track of may not actually be that large. I mean, I'm saying this kind of as an analog to conjugate gradient, but I also feel that in some of these cases, like one can get away with not representing them in kind of a very precise way. Of course, kind of the even more intriguing ones are that algorithms that do get to n to the omega for in the kind of the dense case, they're not even using floating point numbers. They're using some alternate representation, which I would go as far as asking, like, is floating point number even the right way to think about this kind of precision? Because the picture is that we don't have a very basically for the dense case, arbitrary high condition number, non-floats actually beat floats asymptotically. So could some of that technology be brought in here as well?
Mm-hmm, mm-hmm. So we have 2 questions in the chat. Maybe we can take time to look at these 2. So
I really like the first one.
Okay.
Is it possible to multiply the 2 low rank matrices that represent H inverse in less than matrix multiplication time? So to get some kind of explicit representation, this is something we have thought a little bit about, and like this is where the comment I made about multiplying batches of matrices come in. The issue is that you're not like the total size of these matrices still end up being big. I think this is very much related to the second question of, is it possible to get some kind of better number dependence on these things? I feel that is a very intriguing question. For the things we have tried, we couldn't get any of them to work. That does not mean it shouldn't work. Yeah, I don't know. I think this kind of question, like, people have looked at the complexity of inverting dense matrices. I don't think people have looked into the complexity of inverting sparse matrices, especially sparse low displacement rank matrices. Like, I think either way, there's a very interesting question that could be asked about this.
Mm-hmm. And then there was a second question, which seems to just be, why can't you get a inverse also?
Related to the first question, it's basically the related to the first question. It's so let me say a little bit where I'm coming from here. So I took at some point I took a spectral graph theory class, and this is kind of, as Rasmus mentioned at the start, I took there was like a long time I was doing kind of graph theoretic algorithm, but using these spectral stuff, and it started with taking a class on spectral. And so this class, the instructor at some point was talking about eigenvectors, and so I asked the instructor, he was asking us, like, how would you do this algorithmically? And I told the instructor, hey, just do some powering. Essentially, you do some fast powering, or you invert the matrix. And the instructor kind of just looked at me for 20 seconds and just says, never invert a matrix. Oh, by the way, the instructor is Chris Gossel. He actually wrote the book on algebraic graph theories. He actually has a book, Gossel and Royale. That's kind of like the standard graduate text on spectral graph algorithms. But so somehow for myself, it was just drilled into me in a very a very kind of as I'm trying to understand the literature. That was the class where I learned spectral theorem and so on. So somehow I think part of it just I don't look very hard at finding the inverse. Partly because I would just want to never go find the inverse. It does not mean there isn't a good algorithm in this space. I would guess that, if you ask me to put money on this, I would put it at somewhere in between, the inversion complexity and, I would put the complexity of inverting a sparse matrix somewhere between omega and the complexity of solving linear systems. But that's it's not a high certainty kind of bet. I'm slightly inclined to in that direction, but like I would not be surprised if it comes out also to be like n to the omega, like is basically like, because in the dense case we have that these are equivalent, so I would not be surprised in the other direction as well. So short version of the answer is like it's just not something I've looked very seriously at, I feel, and I don't feel like I'm sorry.
Sorry, I was just going to say, I think we're low on time, so let's maybe just say thank you one more time, and then I'll mention that for anybody who wants, we have these, what is it called, informal gathering session that you can click on afterwards if you want to go in, and you can go there and you can video chat with the other attendees if you want to say hello. I'm not sure if Richard will be around, but
I'll be around.
Okay, Richard's going to stick around for a few minutes too then. So you can find these sessions and you can keep talking there. But thank you one more time, Richard. That was very, very interesting.
Thank you.
Okay, so it's our first time using the platform. Let's see if I know how to stop.